A modern factory requires tight precision to run safely. When a manual monitoring system fails, like missing a critical gauge reading, the results are immediate. An industrial water tank can rapidly overflow, flooding the facility, damaging equipment, and forcing a complete production shutdown. To prevent failures like this, facilities rely on SCADA, supervisory control and data acquisition. SCADA is a centralized system that monitors and controls industrial processes automatically, removing the risk of human error from routine tasks. In this tutorial, we are going to build a SCADA project from the ground up. By the end of this video, you will know how to identify the hardware components, map out the digital software logic flow, and execute the exact operational steps to control an automated water tank system. This educational demonstration is brought to you by DEVI Automation Solutions. Learning how to navigate SCADA changes your role on the factory floor. Instead of manually reacting to machinery problems as they occur, you become a system commander who orchestrates and monitors the entire facility remotely. Step 1 is understanding our field components. Out on the floor, we have our physical water tank, a level sensor to measure the water, and a motorized pump to move the water in and out. Next to that equipment sits the local control panel. Inside this panel is the PLC, or Programmable Logic Controller, the physical brain of our system that receives data and sends out commands. Mounted on that same panel is the HMI, or Human-Machine Interface. This digital touchscreen is used by workers locally to check statuses without opening the main electrical cabinet. Moving away from the factory floor and into the control room, we have our centralized software components running on a main computer. This includes the PLC programming environment and the SCADA development software. Finally, we need a communication bridge. We use Ethernet or Modbus cables to physically connect the PLC on the floor to the SCADA computer in the control room. These cables carry all the vital data between our physical hardware and our digital screens. All of these components are required, but they do nothing on their own. They must be linked by a continuous logical loop to achieve true automation. Here in this diagram, you can see a cross-section of our automated tank. Step 1 of our logic cycle begins at the top, where the physical level sensor continuously detects the exact height of the rising water. Step 2. The sensor transmits this raw measurement as a continuous electrical input down the wire to the PLC. The PLC takes this number and evaluates it against the threshold rules we programmed into it. Step 3. The PLC pushes this processed information up the communication cable and into our central SCADA software, which instantly updates the numbers on the HMI displays for the human operators. Step 4. When the water hits our designated full threshold, the PLC executes its logic and sends a physical command back down the wire to automatically shut down the water pump. Read the data, process the rules, command the hardware, and update the screen. This continuous loop is the core mechanism behind every automated industrial process. Now let's look at what the operator actually sees. This is the SCADA Process Overview screen. It provides a bird's-eye digital view of the entire facility, showing our digital tank, piping routes, and punch states all in one place. When we zoom in on the tank-level display, we get the exact numerical readout for the water volume, right down to the liter. Beside it, a simple green indicator tells us the pump is currently active. If an operator needs to intervene, they navigate to the pump control screen. Here, they can switch the operating protocol from auto to manual, bypassing the PLC's automatic rules. Once in manual mode, clicking the Start button sends an immediate override command, forcing the physical pump into action. With a properly configured SCADA interface, a single operator can safely manipulate heavy machinery and high-pressure fluid systems from a secure desk in the control room. Of course, in an industrial setting, physical components wear down, sensors fail, network connections drop, and motors overheat. When that happens, the system must notify the operator immediately. If the pump strains and draws too much current, the SCADA system triggers a motor overload state. The alarm screen takes priority, flashing red warning bars to indicate a critical failure. Standard operating protocol requires the user to review the error and press the Acknowledge button. This silences the alarm, stabilizes the flashing lights, and logs exactly when the human operator responded to the issue. To understand why the failure happened, we open the trend screen. This chart shows our historical water level on the vertical axis, plotted against time on the horizontal axis. We can clearly trace the sharp, anomalous upward spike that triggered our high-level alarm. By logging data automatically, SCADA allows you to review exact operational histories. This replaces reactive guesswork with precise troubleshooting, heavily reducing the time a factory spends offline. You have now seen the complete project cycle. We traced the physical hardware, mapped the PLC communication loop, took manual control of the pump from the digital interface, and used historical data to resolve a system alarm. This exact logic scales up. The same water tank rules we configured are currently running massive municipal water treatment plants, controlling thousands of valves simultaneously. The same principles apply across industries, from oil and gas refineries, smart agriculture irrigation, to massive power generation control centers. SCADA provides the necessary oversight. As automation technology advances, these projects are expanding. Systems are integrating the industrial Internet of Things, utilizing cloud monitoring for off-site access, and applying artificial intelligence to predict maintenance failures before they happen. DEVI Automation Solutions provides industrial automation, PLC programming, HMI development, and complete SCADA solutions. If you found this tutorial helpful, please like the video, subscribe to the channel, and email us at deviautomationsolutions@gmail.com for technical training or engineering projects. By understanding the loop between physical hardware and digital control, you have the foundation needed to operate and optimize the automated facilities of the future.